Hey everybody, welcome to video 2.4. Today we're going to be covering some of the inorganic compounds that are very important to the human body. So this is a little bit of chemistry, a little bit of biology, kind of a biochemistry. Not necessarily review, some of it might be familiar, but just some of these important compounds in general. So if we're talking about inorganic compounds that are important to humans, water obviously has to be the most important. Okay. Water is going to make up to 70% of our body weight. What makes water inorganic or anything inorganic is that it has no hydrocarbons. So these are going to, hydrocarbons are going to be carbons that basically fill any extra bonding spaces that they have with hydrogen. Water is going to be a major component in a lot of our fluids, and we have lots and lots of fluids to worry about. Those fluids typically are going to do things like increase our cushioning, or they're going to reduce friction in the body. So you think like our joints, your menisci, your intervertebral disc, things like that. They'll help reduce that friction or increase cushioning. Water is also a really good place to put heat. So water can absorb a lot of heat and not increase its temperature very much. So in chemistry, we call that a specific heat. So it can absorb a lot of heat, or it can hold a lot of heat without changing your temperature very much. So that way we're not subject to wild fluctuations in temperature. It also serves as our solvent for many solutions. Solution is going to be just any sort of solute. So think like salt or sugar dissolved in a solvent, which is going to be what that solute's dissolved into. Water is considered the universal solvent. So it basically can dissolve anything. And there's some properties of water. It's polar and some things like that. It can serve as either an acid or a base. It can actually do both depending on whether it's forming an OH group or a hydronium group, but it can dissolve almost anything. It's an important part of colloids, which are basically going to be a solution that has particles in it that are dissolved, but those particles are big enough that it starts to make the water look very cloudy, and they're going to not be dissolved very well in that solution. And it's going to be an important part of suspensions, which is where you have particles that are even larger than that, which you have in colloids, where they're basically suspended in water, but if you give them much time at all, they're going to start settling out of water or falling to the bottom. Water is also going to be involved in two of our chemical reactions that we'll see: dehydration synthesis and hydrolysis. So here we can see a picture of dehydration synthesis and hydrolysis. They're essentially the reverses of one another. In dehydration synthesis, we're taking an OH group and a hydrogen from two different substances. We're forming a water by pulling those out, and as a result, that oxygen is going to form that bond in between the two substances, and we end up removing water out of the system. And then in hydrolysis, we're going to add a water to the system, and it's going to come in, and you're going to add a hydrogen to this oxygen and an OH group to the other monomer, and it's going to end up splitting your substance. So dehydration synthesis, we're removing water from the system, but it's a synthesis reaction we're building. And a hydrolysis, hydro meaning water, lysis meaning to cut or to split or to burst, we're using water to split apart those two monomers. Okay, another inorganic compound is your salts. Salts are going to be any basically group 7, your halogens bonding with a group 1 element. Those are typically what we would consider your salts. They are going to be completely dissociated in water. So they dissociate into what we would call electrolytes. You have your like your sodium, it has a positive charge, chlorine has a negative charge when they're dissolved in water. They do separate from one another, and they end up being surrounded by water, which you can see in these pictures here. But they are going to be an important part because obviously we need salt in our diet, but we also need these electrolytes for a lot of body functions. Acids and bases, they're going to dissolve in water, or they're going to dissociate to come apart in water just like salts do. Your acids, when they do that, they're going to release hydrogen ions, and your bases are going to release hydroxyl ions. So hydrogen ions are H+, hydroxyl is your OH- groups. The more hydrogen ions you have, the stronger the acid is going to be. Or if you wanted to flip it around, not very many people talk like this, but you can say that the more OH groups that you have, the stronger the base is going to be. Usually we'll talk about it in terms of hydrogen. The more hydrogens you have, the stronger the acid, or the more hydrogens that can be accepted by the group, the stronger your base. And we can measure the strength of an acid or a base based on the pH scale. pH is basically going to be the negative log of your concentration of hydrogen ions. And how it works, logs, and this is a base 10 log here, so just your normal log, work in powers of 10. So a pH of 4 and a pH of 5, they're going to be a 10 times difference between those two. So a pH of 4 is going to have 10 times more hydrogen ions than a solution that has a pH of 5. Typically, the scale runs from 0 to 14, with 7 being right in the middle. Pure water is 7, because remember, water can act as both an acid and a base. It's going to sit right in the middle. Lower numbers are more acidic, higher numbers are more basic or more alkaline is another word for this. An important part with acids and bases is to talk about buffers, especially in the human body, and homeostasis, because the body wants to keep you at the exact right pH at all times, especially with something like blood, which is super important to stay exactly at 7.4 pH. Buffers are a way, they'll have a weak acid and a base version of that acid, and they're going to be responsible for keeping your pH at the right levels. So this weak acid, weak base, or this weak acid base buffer, if you have a solution that starts getting too basic, the weak acid is going to start donating hydrogen ions to make it go back to the right pH. Or if the solution starts getting too acidic, it has the ability to start accepting those hydrogen ions to remove them from the system, and the base is going to correct that system back to the correct pH. So here you can see how this, the acid base in the water here, the hydrogen ions. What I like better here is this acid to base pH scale. Here you can see all the way from a 0, which is going to be things like battery acid and pure hydrochloric acid. Lemon juice and acetic acid or vinegar have a pH of about 2. Tomatoes are about between 2 and 4, so you have tomato juice here around 3. Coffee about 5, all the way up to blood, which is exactly 7.4 and needs to stay at 7.4. Otherwise, you start running into all sorts of issues. Seawater with all that salt brings its pH to 8. You get baking soda, ammonia, pH around 11, bleach 13.5, liquid drain cleaner close to 14. Okay, so that is supplementary video 2.4 on inorganic compounds. That one, this video is pretty short, I went through it kind of quickly. So if you have any questions on the chemistry or anything like that, please